we have now had 2 lessons on deterministic data flow concurrency, introducing the basic concepts, the semantics, and showing a number of programming techniques and examples. So, what can we say about deterministic data flow? Well, it's actually a form of functional programming, a concurrent generalization of functional programming, and it keeps the good properties of functional programming. Confluence, which means that independent of what order you execute things, the result is the same. Referential transparency, replacing equals by equals, just like in algebra. Well, this also holds for deterministic data flow. There is no observable non-determinism. In other words, no race conditions. It means a concurrent program, when given the same input, will always return the same results. This is a very strong property of concurrent programs. We can use higher order program. All functional programming patterns will be lifted into the concurrency regime and will give you concurrent patterns in deterministic data flow. This is an extremely powerful way of leveraging all the techniques of functional programming. We can also say that concurrency is transparent. This is what I call concurrency for dummies. It means you can add threads anywhere you want, in any number you want, in a functional program or in a deterministic data flow program, and the result will not change. The only thing that will happen is the program will become more incremental the more threads you add. In fact, you can consider a thread as a unit of weighting. If I were a billionaire and I needed a loaf of bread, I would send my butler to the bakery to wait in line. The butler is a unit of weighting. Okay, so in that same way of looking at things works for threads. A thread is a unit of weighting, and you can add as many as you want to a program to remove roadblocks and make the program more incremental. So that's another point. The final point is non-determinism. Okay, you still need non-determinism. The real world is non-deterministic. Client-server application, for example, is a simple application that we see where you need non-determinism. So how does that combine with deterministic data flow? Well, it's very easy. The deterministic data flow should be the default. That means by default, we are in this very nice paradigm, and we will add non-determinism exactly where we need it, and only there, and nowhere else. So in a client server, for example, there's only one point where you need to add non-determinism. That's where the server waits for a client request from any client. And the consequence, deterministic concurrency is seeing a well-deserved resurgence after decades of neglect. In fact, it was invented in the 1970s. It's resurging both at large and small scales. Big data computing in cloud data centers, multi-core computing, all of this introduces huge amounts of concurrency that is very difficult to control. So the deterministic data flow default is a very good default, and it's being used. Okay? So, where do we go from here? Well, there are many more things to learn about concurrency. For example, there are other paradigms that avoid race conditions. In addition to the deterministic data flow we saw, there is also the lazy version of deterministic data flow. This is a version that uses what's known as by need synchronization. It only calculates the results that are needed to make the output, and this is determined during execution. So an infinite loop will only execute the number of iterations that's needed in order to calculate the output, for example. This is explained in chapter 4. You can see this in the CTM textbook. Another paradigm that avoids race conditions is called constraint programming. This is actually probably the most powerful paradigm for deterministic concurrent programming, since constraints are logical conditions and we're in some sense doing equation solving on constraints. This is actually generalizing logic programming. The Prolog language, logic programming, which was invented in the early 70s, has generalized now to constraint programming, and operations research algorithms have been merged into this, making this a very powerful paradigm for solving complex combinatorial problems. That's the third thing. Another thing is secure distributed programming. In a secure distributed system, you have to manage non-determinism as well. And there I would like to mention the E language. E, which is a language for secure distributed programming, secure in the sense of cryptographically secure, using the notion of capabilities in the language. That is also very strongly related to concurrency, deterministic concurrency. And in addition, we have also paradigms that can express non-determinism. They are the message passing paradigms, and they are the shared state paradigms. These are the two main families of languages and approaches for doing concurrent programming. The message passing paradigm is in fact significantly easier to use than the shared state paradigm, and this is the one that is coming more and more into the forefront, in particular with Scala and Erlang, but also other systems. And the shared state paradigm, which is based on monitors. Monitors are a way for threads to coordinate and access shared data, and also transactions. Transactions are a way of doing large atomic operations on data. So transactions are very nice for databases. Monitors are a more questionable concept. I would only recommend them in legacy systems and not in new systems that you use. So, finally, what can we say about a really good paradigm for concurrent programming? In fact, we can combine deterministic data flow and message passing in some sense to get the best of both. This is using the straightforward technique of extending a paradigm that we have done several times in this course by adding a new concept to get a new paradigm. We add one concept to deterministic data flow, which is called a port or a named stream. So essentially, all we're doing is adding the ability to give a name to a stream. So instead of having a stream being just a list that you can build inside a list function, here we have a stream that has a name, and you can send a message to this named stream, to the port, and the message will appear as an element on the stream. And since any thread can send a message, because the thread just has to know the name of the stream, so any thread that knows the name can send a message, this adds non-determinism. Okay? So this is a way of adding non-determinism. And since the named stream is still a stream, it can be used in all the deterministic data flow programs that exist. So it's a seamless way of generalizing deterministic data flow. And this is what I call multi-agent data flow programming. It allows adding non-determinism only where you need it. It is a very powerful and concise paradigm for writing concurrency patterns. So for example, the contract net protocol, which is a simple negotiation protocol where a buyer sends requests to n sellers. Each seller returns its quote for a particular thing to buy, and then the buyer accepts the best and rejects the other. So this requires a number of messages to pass between buyer and sellers. This can be written in just 3 lines using higher order combined with named streams. We've actually done an experiment to add this to Scala. We have designed and implemented a language called Ozma, which essentially extends Scala with all the multi-agent data flow concepts of Oz. And we've actually presented this at some industrial conferences, and it worked quite well, and people were very interested in it, except that it was only a partial success, but because it requires fine-grained concurrency, cheap threads. In the deterministic data flow program, the idea is that threads are very simple things, and you can use them very often for very small computations, but this does not fit with the JVM, the Java Virtual Machine, on which Scala is implemented, which does not have support for fine-grained threads, or not right now. It may be in the future, but not right now. So this was only a partial success since we had to implement Ozma on the Mozart virtual machine in order to get the fine-grained concurrency. So in our view, in mine and also Saif Haridi's and some other people's, multi-agent data flow is the best all-around paradigm for doing concurrent programming. It's even better than another good one, which is Erlang, because multi-agent data flow allows managing non-determinism. And that's why, since we consider this really the best paradigm, we consider it would be really, really a shame if we would not present this in more detail in this course. That's why that multi-agent data flow will be the topic of the next lesson, the bonus lesson given by Saif Haridi.